Hello there and welcome to the video that I've prepared for Chapter 14, discussion of concepts associated with equilibrium and equilibrium constants. And I'm trying to bring two classes to the same point here. So as I suggested to one of my classes, this first couple of minutes might be a little bit of rehashing what we did at the end of our last class. But for other students watching, this might be brand new material. Three main goals to accomplish in the video segment today. One is to either revisit or introduce the concepts of Kp and Kc, equilibrium constants expressed in terms of pressure or concentration, the two different properties that we can use for that. Introduce a new idea called the reaction quotient and its importance, as we'll see. And then finally, the bulk of our time today will be spent looking at problems and examples of reactions with equilibrium constants and how we use the equilibrium constants in a reaction setting. Okay. So we have two different ways of expressing our equilibrium constant. One in terms of concentrations of products raised to their coefficients from the reaction, divided by the reactant concentrations raised to their coefficients. Or we could do this for pressures, where we would take the pressure of our products raised to their coefficients divided by the pressure of our reactants raised to their coefficients. And really the question is, are these two numbers the same thing? The idea they're the same thing, but are they actually the same value? And we use the ideal gas law to prove that they are not the same thing, because pressure is not exactly the same thing as concentration, but they are related. The relationship between Kp and Kc then is determined by how many factors of RT you have if you were to relate these two expressions to each other. And so it's quite simple. The pressure-based equilibrium constant is the concentration-based equilibrium constant raised to an exponent delta n. This delta n is the difference in the moles of gas between the product and reactant side of your reaction. So if we had a reaction like ammonia production, N2 plus 3H2 to produce 2 moles of NH3. The delta N for this reaction would be 2 minus 4, or negative 2. This 2 is coming from the NH3 on the product side, and this 4 is coming from the 1 plus 3 of the nitrogen and the hydrogen. So it's the total moles of gas on each side of the reaction. If I told you that the Kp for this reaction was, for example, 5.8 times 10 to the positive 5 at 25 degrees Celsius, we could use this formula that we've just developed to find the concentration-based equilibrium constant. Now, as I look ahead to my answer, I know that it should still be a large value. This is a significant equilibrium constant. Remember, putting it into the context of comparing it to the number 1, which means that this reaction is product favored. Regardless of what I start with, a bunch of this stuff or a bunch of ammonia, this system wants to end on this side. It wants to have a lot of ammonia present in it. And it doesn't matter if I'm talking in terms of pressure or concentrations up there. It should be the same idea. It should still tell the same story that this is a product favored system. Okay? So I'm just thinking about what my answer should be before I dive into the calculation. All right, to find Kc, I have to take this equation up here and manipulate it a little bit. Kp must be divided by RT to the delta n. So in this case, Kp was 5.8 times 10 to the 5th, divided by R. I'm using the ideal gas constant version of R, 0.08206 atmosphere liters per mole Kelvin, and the temperature. The temperature needs to be in Kelvin because the units of R are involve Kelvin. And then that expression is raised to the -2 power. This -2 coming from the delta N calculation that we did up here. It won't always be -2. You have to figure that out for each and every reaction that you're looking at. Right? Make sure you follow your order of operations. First, you do this multiplication inside the parentheses, raise that to the -2 power, and take the equilibrium constant divided by that. And we end up with 3.5 times 10 to the 8th as our equilibrium constant. Okay? Now, I don't need units on this. Normally we would, and units do exist. The equilibrium constant units for this reaction would be 1 over molarity squared. The units for the initial Kp would have been 1 over atmospheres squared. But because the units change when we change languages from concentration to pressure, and the units change with every single reaction based on the coefficients, how many molarity units stick around, or how many atmospheres stick around in the case of a Kp, we often don't bother writing the units on a Kp or a Kc. So it's the one time, again, that you're sort of forgiven and don't have to worry about that. Okay? All right. Let's move on to this next concept of what a reaction quotient is. Suppose you went into the lab and you wanted to conduct a reaction. Keep it real simple. This reaction is going to be A turning into B. This is a reversible reaction now, though. The question I have for you is, how will you know when you have reached equilibrium? How are you going to know when this reaction has achieved equilibrium? Are you going to sit and watch it constantly? Are you going to leave for an hour and hope that when you come back it's reached equilibrium? How can we know when any reaction, for that matter, has achieved its equilibrium state? Well, we want to remember that at equilibrium, based on what we talked about in our initial discussion, at equilibrium we will observe steady state concentrations. Right? The piles of A and the piles of B, they're going to be changing at the start of our reaction up until the point where we reach equilibrium. And so if we can monitor the concentrations, we will see them changing over time. And then when they stop changing, that's when we know we've reached equilibrium. But that's also going to be a way to find the equilibrium constant of this reaction, in any reaction, if we didn't know it in advance. Okay? So as an example, what we would do is we would collect values for the concentration. How many A's do we have and how many B's do we have in each of these instances? So imagine that I began my reaction and that the first time I measured it, I had 1 A and 499 B's. So I'm actually starting with a lot of my products and very little of my reactants. Right? And then I stepped out of the lab and I came back a little bit later and I was up to 100 A's but down to 400 B's. Come back a little bit later and my A has jumped up to 180. My B is down to 320. A little bit later, I'm up to 200, down to 300. Then I'm up to 210, down to 290. Come back later, I'm at 210, 290. Even later, 210, 290. So this is my steady state. These concentrations are no longer changing. Now the equilibrium constant of this reaction would be the concentration of B divided by the concentration of A. So down here, that would be this 290 divided by 210, which is 1.38. So I have observed what the equilibrium constant is. I've discovered, if I didn't originally or previously know what it is, what the equilibrium constant of this reaction is. Okay? But there's a lot of good stuff going on right here as well. We're watching this reaction bring itself to equilibrium, if you think about this, over time. All right? And what if I had done this exact same recipe of how much B divided by how much A I have at each of these other times that I studied this reaction? I would have 499, and then I would have 4, then I would have 1.78, then I would have 300 over 200, which is 1.5, and then I would have finally my 1.38. It is not coincidence that this number is systematically getting smaller and smaller until it equals the equilibrium constant. And in fact, we have a name for all of these values. We would call them Q, the reaction quotient. All right? It is the equilibrium constant essentially at a time prior to establishing equilibrium. But following this reaction quotient tells us when we've reached equilibrium. If we graphed this, we would see that a graph of Q versus time, in this case, would have gone from a very high 499 all the way down until this steady state value of 1.38, which is K. So the long story made short here is that Q becomes equilibrium constant, the KEQ, all right, when equilibrium is reached. But it also gives us a little bit of insight as to what's happening to reach equilibrium. In this example here, at the start, Q was significantly larger than the equilibrium constant. All right? And what happened was Q had to get smaller so that it could equal the equilibrium constant. Now, physically, how that happened was, look, we shifted products over to the reactant side. In each case where we were checking in on these ratios, the amount of products was decreasing and the amount of reactants was increasing. So we were trading products for reactants. The reverse reaction, the B to A, is what makes that happen. So anytime now that you check in on any reaction and Q is bigger than the equilibrium constant, your reverse reaction is the one that is occurring to bring you to equilibrium. Now they're both occurring, but it's occurring more rapidly to bring the system to equilibrium. Okay? Another way of saying this would be, during this time when Q is greater than K, you are forming reactants. Right? That's what the reverse reaction does. Or you're consuming the products. On the other hand, we could also have the case where Q is less than our equilibrium constant. If we had flipped these numbers and started with a 499 and a 1, Q would have been extremely tiny, and then it would have come up until it reached K. So Q still would have become K, but from the other direction. The A would have had to decrease. The reactants would have decreased in order to increase the product amounts until we were at our equilibrium condition. And so that would be the forward reaction occurring. So these two belong to the first case of Q greater than K. So the forward reaction is more rapid, or we are forming products. This is how we can use this reaction quotient. It's like a map or a compass, maybe more appropriately. It tells us which way our reaction needs to proceed to get to our final destination, which is always the equilibrium constant. This system, B over A, wants to get to this ratio of 1.38. So regardless of where I start, it's going to shuffle A's and B's until it gets to 1.38. It's our compass, like I said, that can help us decide what's going to happen. So let me put it into the context of an example with a real reaction. Two nitrogen dioxides, 2NO2, producing an N2O4. At some temperature, 298, fair in this case, the equilibrium constant for this reaction in terms of pressure, Kc, is 170. So, if you mix, all right, if you mix 0.015 molar NO2 with 0.025 molar N2O4, which species will, let's say, increase, okay, in order to achieve equilibrium? Okay. Now I know I'm not at the equilibrium constant because the equilibrium constant for this would be N2O4 concentration divided by NO2 concentration squared. If I try to calculate this number from these concentrations that I'm given right now, 0.025 divided by 0.015, that which needs to be squared, this equals just 110. So this is not the Kc, which is 170. So this number is a Q, just like in the table that I just had up here a minute ago, right? This is, I checked in on this reaction at a time where I'm not yet at equilibrium. Well, actually, it's what I started with, right? Okay. So now this is my compass, this Q. Q, 110, is less than the equilibrium constant, 170. I need this number, this 110, to grow until it equals 170. The way that's going to happen is to what? Increase my numerator, decrease my denominator. My numerator is my products. My denominator is my reactants. So how is that going to happen? If the forward reaction occurs, right? More. So if NO2 turns into N2O4, that'll bump up this number, bump down the denominator number, and the overall result would increase until we reach 170. So anytime Q is less than Kc, the forward reaction is going to occur. And as a result, to answer the question the way that it was asked here, which species will increase, the N2O4 will be increased in this case. But the question could have been, how will N2O4 change? Answer, it'll increase. How will NO2 change? It will decrease. So there's a variety of ways that the question could be asked, all answered by comparing the Q value, the current value, current state of affairs for this reaction to the equilibrium constant, where we will ultimately end up. All right? So that's how we can use this reaction quotient. It's helpful in finding experimental equilibrium constants because we know it becomes the equilibrium constant over time. But it's also helpful in understanding what will happen when we mix certain quantities of chemicals in a reaction. All right, now we're ready to head to the types of actual equilibrium problems that we're going to do. There are two broad categories of equilibrium constant problems, right? And we're actually going to do the same two broad categories for the next 2 or 3 chapters. We'll just put a different spin on each of them for the specific context in which we're going to be working. So the first category of problem would ask you to find an equilibrium constant. To find an equilibrium constant, you need to know something about how much of your chemicals you have at equilibrium. How much products do you have? How much reactants do you have? So you can substitute those numbers into the equilibrium constant expressions, which we've had a lot of practice writing so far. On the other hand, a more practical use of an equilibrium constant, we often know them, we can look them up in books, online, is to use that equilibrium constant to predict what the concentrations or pressures of your chemicals will be when equilibrium is established, right? And this is the problem that takes the place of the traditional stoichiometry methods that we were learning and using in Chemistry 1. So I'm going to walk you through a few examples that cover each of these types. And we're going to introduce an entirely new type of problem-solving strategy to help us organize what seems like many pieces of data that we might have in in these reactions. Okay? All right. So here's our first one that we want to do. Consider the reaction where phosphorus pentachloride, PCl5, decomposes into PCl3 and Cl2. Okay. If you begin with 0.15 molar PCl5 and allow the system to reach equilibrium, okay, allow the system to reach equilibrium, you find the chlorine concentration, Cl2 concentration, is 0.08 molar. What is Kc then for this reaction? All right. So I'm keeping this space blank for a second intentionally. So how would we find the equilibrium constant? Well, we always want to start with an equilibrium constant expression. For this reaction, that would have the concentration of the products, PCl3 times Cl2, divided by the concentration of the reactant. Nothing is raised to any exponents because all the coefficients are 1. So it's simple enough. We just need to know what are the 3 concentrations at equilibrium. All right? And that's the trick. One of these numbers is an equilibrium concentration. For chlorine, the concentration is 0.08 at equilibrium. But the 0.15 is not the equilibrium concentration of PCl5, right? It's what we begin with, the initial, right? Big pile of PCl5, but we're getting rid of some of that to make the chlorine on the product side. and also to make the PCl3. And it's that idea of we can track how much comes off of this pile, so to speak, to form these piles over here. That's going to tell us how much is left, or what the equilibrium concentration is, right? So we're going to set up what's called a reaction table to lay out this data, all right? I'm going to keep track of the initial concentration of each chemical. Then I'm going to keep track of what's the change, the delta, to each concentration. And then finally, what is the equilibrium concentration of each chemical? And it'll be this row that's the most important. This equilibrium row, the three values that we get, go over here to the equilibrium constant expression. All right. Now, in the equilibrium constant table, what's really nice is that the initial concentration plus the change in concentration equals the equilibrium concentration. So under each chemical, we're going to have a very simple addition problem, or subtraction problem perhaps. Okay? So that's one thing we want to keep in mind for the change row. The other thing is, or for the equilibrium row, the other thing to keep in mind that's very important is that the delta concentration row values must be in the same ratio as the reaction coefficients. In other words, if I take one PCl5 off my PCl5 pile, I know I have added one each. Notice how I broke the pen from its cap, right? If that's a PCl5, I've formed one PCl3 and one Cl2. It's a 1 to 1 to 1 relationship in this case. And that is crucial to solving these values, for the values. All right, we're ready to start then. We know the initial concentration of PCl5. It was 0.15 molar given to us. It is safe to assume that these two values are 0 because they are not mentioned in the problem over here. And it's the only way that this problem can be fair, right? Now I know sometimes you think I might ask some tricky questions or might be setting out to set up a trick question, but that cannot happen. Either we know the amount of each species, or it is assumed to be 0 at the start of these reactions. Okay, so we could put a 0 there. The only other number that we know is that at equilibrium, our chlorine is 0.08. So I've used the two numbers from the problem and then this safe assumption that these products start at 0. Now I'm going to use these two ideas that I laid out below the table. In the chlorine column, right? Well, the only way we can get from 0 to 0.8 is if we increased by 0.08. So I actually found the 0.08. It's much easier than thinking about it in terms of this equation, right? But you could say I solve for the delta here by taking the equilibrium minus the initial, right? But it's pretty obvious that the only way to get from 0 up to 0.8 is to add 0.08. That then propagates a series of other numbers. Because the chlorine and PCl3 share the same coefficient, each time my reaction makes a chlorine, it also makes a PCl3. So I know that these two change by the exact same amount. Also, this would be the amount that the PCl5 decreases by. So I put a negative sign in front of that. So I've got negative, not sure if the blue's showing up very well. So I've got negative 0.08 for the PCl5 and positive 0.08 each for my PCl3 and Cl2. Don't be confused that you're thinking this whole row should equal 0. Okay, I caught the video cutting off, so I think it was cutting off and getting restarted. Just looking at this middle row of the reaction, there's a tendency to think, shouldn't this be like a net 0 here? No, remember these numbers have to match the ratio down here. This reaction tells me each time I take a PCl5, I will make a PCl3 and a Cl2. That's what those numbers are, the same values. But they have to be opposite in signs. The reactants are going to decrease in this case, and the product piles are going to increase. Now I can work in each column. Just like I worked in chlorine at the start, well now I can take 0.15 minus 0.08, and I see that I'll have 0.07 molar PCl5 left. And then I'll have 0.08 molar PCl3 formed. Take these numbers over here, and I'm ready to get my equilibrium constant. 0.08 times 0.08 divided by 0.07, and this equals 0.091. That is the equilibrium constant of this reaction. Okay? So these reaction tables, you might have been able to sort these out in your head. Lots of folks, with just a couple of numbers can keep track of them. But the table is a consistent, reliable, systematic way for you to organize the reaction quantities into these three categories. What you start with, what happens during the progress of the reaction, the change, and what will you ultimately have at equilibrium? That's what's connected to the equilibrium constant. All right. All right. Let's do a next example. This one will go in the opposite direction. We'll start with an equilibrium constant, and then we will determine an equilibrium concentration. Now this one will be very straightforward, and then I'll show you a more sophisticated version of it. It's not quite as simple. Here's a reaction: methane CH4 plus water vapor H2O, a reversible reaction to produce carbon monoxide and 3 moles of hydrogen gas. At 1200 Kelvin, pretty high temperature, the equilibrium constant is equal to 0.26. This is going to be a Kp because everything is in a gas phase here. I'll go ahead and use a Kp. All right. A flask containing this reaction is at equilibrium. If the following pressures are known, what is the pressure of the water vapor in the flask? Okay. So the equilibrium constant expression is once again crucial to solving this problem. The expression that relates how these chemicals are all tied together at equilibrium. The pressure of carbon monoxide times the pressure of hydrogen cubed divided by the pressure of methane and the pressure of water, since we're doing this in terms of P values. Okay? There are 5 values here. We know 4 of them. Oh, I didn't write them down. Here are the following pressures. At equilibrium, we know the pressure of carbon monoxide, CO, is 0.81 atmospheres. The pressure of methane, CH4, is 0.13 atmospheres. And the pressure of the hydrogen is 0.28 atmospheres. So of the 5 values that we've got in this equation right here, K, and then the 4 respective pressures, we know 4 of them, and we can solve for the 5th one. The one we don't know is the pressure of the water vapor. So algebraically, I'm going to solve for the pressure of the water vapor. And really the Kp and the water vapor just switch places. Pressure of carbon monoxide times the cube of the pressure of hydrogen divided by the pressure of methane and the Kp value. And here it's just simple plug and chug. Carbon monoxide, 0.81 atmospheres. Hydrogen, 0.28 atmospheres. That one needs cubed. Don't forget to cube it. Methane, 0.13 atmospheres. And then our equilibrium constant, 0.26. All right. Now I haven't included the units here, but there would be units there, and they would be in the correct set in terms of atmospheres, so that our answer would equal atmospheres. So this is going to be 0.53 in the end, atmospheres. Okay. So that's one way that we can use an equilibrium constant to figure out the concentration or pressure, in this example, of one chemical at equilibrium. Okay? This one's not that tricky, to be honest. And you might be asking the question, well, why couldn't you just measure water? You were able to measure everything else. Why couldn't you measure water? Sometimes you might not have the right equipment to be able to measure the concentration or pressure of every species that's present. And so this would be a different way. If you could calculate or measure everything but one, you could calculate the missing piece of that puzzle. All right. All right. What if we didn't know anything at equilibrium? Like in that example, I knew all but one of the equilibrium concentrations. What if we didn't know any of them? Could we calculate all of the equilibrium concentrations or pressures in a system? All right. So this next example will walk us through how we would do that. All right. N2O5 gas to N2O3 gas plus O2 gas. At 800 Kelvin, the equilibrium constant, Kp, is 6.35. If you begin this reaction with only 0.600 atmospheres of N2O5, what is the equilibrium partial pressure of each species? How much of everything are we going to have? Unlike the last example where we just were asking about the water because we already knew the other 3 chemicals, now I don't know, and I'm not telling you how much of anything you're going to have at equilibrium, and you're going to have to find it out. So the key to solving this problem is going to be to use a reaction table, all right, and to think a little bit outside of the box to represent the changes with a variable, as you'll see in a moment. So what if I were to try to set up a reaction table like we did a few minutes ago? This time I would do it with pressures, initial pressure, the change in pressure, and the equilibrium pressure. I could put in the 0.6 atmospheres as my initial pressure. And again, fair assumption that these two are each 0, right? That we have none of the products because we're only told about the reactant N2O5. Right? Now, again, it's pretty obvious something's going to happen here, right? That's why there's a reaction written. We're not just wasting our time here. So what's that something? The key is that we know that some of the N2O5 will react. But how much is the question? Well, we're not exactly sure. But that's where this idea of using math to help us out, algebra to help us out, really does become a benefit. This language of some or an unknown amount of N2O5, that can be represented by a variable. So I could say that some of the N2O5 will react. So minus X. Because of the relationships, again, remember the delta P numbers match the coefficients ratio. So if N2O5 is going down by X, both of these are going up by X. All right? Not getting us too close to our answer yet, but then at equilibrium, if I knew what X was, the amount of N2O5 that's left is just 0.6 minus it. And the two products are just X. All right? So some of the N2O5 will react. We represent that amount with an X, and then we finish out our table in terms of the X values. Now, how do we find X? We're going to find X from the equilibrium constant expression, right? So what is our equilibrium constant expression? Kp is the pressure of N2O3 times the pressure of oxygen divided by the pressure of N2O5. Just like we've been writing, products over reactants. Again, no coefficients to become exponents here, so we're in good shape. Well, earlier we had some numbers when we were finding these things, but now we've got some variables, but that's not a problem. 6.35 equals X times X over 0.6 minus X, or X squared equals, now I've multiplied this over to the left side, 3.81 minus 6.35x. Algebraically now, I have a polynomial. 0 equals x squared plus 6.35x minus 3.81. Really, the only way to solve this polynomial for the two values of x that make it true. There are two numbers for x that when I plug them in right here will make the right side equal 0. And this becomes a true statement. 0 equals 0 then. They're the roots of a polynomial, right? There's some graph here, that we're trying to find those roots. Okay, yeah, this is all algebra at this point. So we kind of lapsed into an algebra mode so that we can get the answer to our question over here. Okay, so the quadratic formula, and not something you need to have memorized, it's on your formula sheet. Some people have it pre-programmed into a calculator or something like that. That's all fine, but we need to be able to use it. So let's not make a bigger deal out of it than we need to, all right? But it's negative b plus or minus the square root of b squared minus 4ac over 2a, where a, b, and c are the coefficients when your equation is written ax squared plus bx plus c equals 0. So here the a is 1, the b is 6.35, and the c is negative 3.81. So if you haven't done this in a while, get ready to practice and use this formula. But when I do this, I'll get two answers for x, right? Because logically, this polynomial has two roots. So the two answers that I get here are 0.552 and negative 6.90. Now, while algebra says there are two answers to this polynomial, two roots to this polynomial, chemistry says that only one is the answer. Only one of those values is the actual answer to our problem of what is the pressure of some of these chemicals at equilibrium. All right? And that's where thinking about our answer ahead of time would have been useful. So I haven't done that yet, but based on this idea right here, this tells me the limits of my answer. That x has to be less than 0.6, right? Because if it's bigger than 0.6, this would predict a negative pressure for the N2O5, which doesn't exist. So that limits it. And x also has to be bigger than 0. Otherwise, these things would still be 0. So I've put some boundaries on my answer, actually. Thinking about the values that x can potentially be that make sense from a realistic perspective of how this reaction and chemicals have to behave. So in that context then, only x equals 0.552 makes sense. The negative is, it's not that it's a negative, it's that it's out of the range of good options for our problem over here. Sometimes the way your algebra is set up, the negative might be the correct answer. Sometimes you might get two positive numbers, all right? So you have to decide, not just by throwing out negative all the time, but rather you have to decide by looking at those numbers in relation to what are the reasonable range of numbers for your answer. Now that I know what x is, let's come back over and finish this off. Here's our answers. 0.552 atmospheres, 0.552 atmospheres. That's what the pressure of N2O3 and O2 is going to be. And then this one is going to be 0.048 atmospheres when we subtract. So I really just added a fourth row here. And these are the answers to our problem. Okay? So we find ourselves needing the quadratic equation sometimes, not all the time. I'll do another example, a couple of other examples where we won't necessarily need the quadratic formula, quadratic equation to solve. It's all dependent upon the coefficients and how they stack up in the equilibrium constant expression. All right, I'm going to pause right here for a second, and the video will pick right back up with our next example. Okay, I'm back and ready to do our next example of using an equilibrium constant. It's going to look very similar to the last one that we just wrapped up, except that the math's going to maybe get a little bit uglier, and we're going to try to think about a creative way to solve this problem without having to do what at first glance appears to be some pretty challenging mathematics or algebra. Okay? I really am interested in keeping life simple for you guys, believe it or not. Sometimes it's easier to use the quadratic formula like we just saw, and then sometimes there's no way around it, or is there? We'll see. So set the stage, the new reaction here. 2 hydrogen sulfides, 2 H2S's, will produce 2 hydrogen H2 and an S2. Let's get an equilibrium constant, Kc, 1.08 times 10 to the negative 7 at 298 Kelvin. Okay? Just as we had in the last problem, let's say we have an initial H2S concentration of 0.800 molar. Let's find all the equilibrium concentrations. So our last example, we began with the initial pressure of a gas and we were finding all of the equilibrium pressures. This one we're starting with the equilibrium concentration of our reactant and going to the initial concentration of our reactants, what we're starting with, and we're finding the equilibrium concentration. So very, very analogous. We're just using concentration this time. All right. So the same idea. Let's work with an equilibrium table right away. The same ideas exist here in that we have a little bit of information about where we're starting this reaction. 0.8 molar H2S. And then we have none of these, it's safe to assume, because they're not mentioned at all. Right? Now once again, some amount of the H2S will react just like the last reaction where some amount of the N2O5 reacted. Now here, might not want to write this down just yet. If I say that X of the H2S disappears, then it's fine that also X of the H2 will appear. But the quantity of sulfur will only be half of that because of the 2 to 2 to 1 ratio. And this row must match the three numbers. 1/2, 1 to 1 is the same as a 1 to 2 to 2 ratio. Now, if you don't like decimals and fractions and things, you might want to figure out a different way around that. So a classic thing to do is to just match the coefficients. Minus 2x plus 2x plus x, and have these numbers just immediately match the coefficients in your reaction. All right? And that would mean that at equilibrium, sulfur will be x, hydrogen will be 2x, and hydrogen sulfide will be 0.8 minus 2x. So far, so good, right? Looks pretty similar to what we had last example where we created this x to represent the amount of reaction that will occur. Okay? Now, we found that x by writing an equilibrium constant expression and then solving for it. Let's see what we can do this time. The Kc for this reaction would be the concentration of hydrogen squared times the concentration of sulfur divided by the concentration of hydrogen sulfide squared. So I've just taken my coefficients, they've become the exponents, products over reactants. That is what is going to make this problem start to look a little bit ugly though, because hydrogen is 2x and then it's going to need to be squared. Sulfur is x as its concentration, and hydrogen sulfide is 0.8 minus 2x squared. All this equals the 1.08 times 10 to the negative 7. Now, I've got some simplifying to do, just like I tried to do last time before I got into the quadratic formula. This numerator would become 4x squared times x, which ultimately will become a 4x cubed. The denominator is where I really get into trouble though. I've got to square this binomial out, right? Remember your FOIL method? First outer, inner last. So I'm going to get 0.64 minus 3.2x plus 4x squared as my denominator. All that's still equal to the 1.08 times 10 to the minus 7. Ultimately, this is going to equal, when I take the denominator over, and I am doing this very quickly because I'm going to get rid of this in just a second, all right? But when I take the denominator over, like I did last example, and then combine all my terms together, I will end up with an equation that looks like this. 0 equals 4x cubed minus 4.32 times 10 to the negative 7x squared plus 3.46 times 10 to the minus 7 x minus 6.91 times 10 to the minus 8. Okay? You cannot use the quadratic formula to solve this, because it's not a quadratic. that name quadratic formula is not a coincidence. It is implying a second order polynomial. Quadratic sort of belongs to second order polynomials. This is a third order polynomial, as we see right here. All right? And this is a much more complex problem to solve if we are, looking, to factor this out like we did with the quadratic formula. All right? Now, we actually don't need to get to this point because we've made an error. We haven't thought about our answer and we haven't thought about our system before we jumped in. Classic trap. We learn how to do something once, we get a next example, and we want to try it the exact same way. So we saw the last example where we made up these x's, all right, and then we just plugged them in and processed that equation using the quadratic formula. It won't work here though. And what we needn't get to this point because we failed to think about something very important here. So I'm going to erase all of this. Get rid of it because I'm not going to need it. The key to solving this problem, and what you always want to do when you're given a problem, is you want to consider the size of your equilibrium constant. Remember, one of the first things that when I introduced these equilibrium constants was I talked about their significance, whether they're large or very small. This k, 1.08 times 10 to the minus 7, is very small. That's not just, fact, let's just say it's small. That has a significance. The significance of that is that this is what we call a reactant-favored reaction or system. The subtext here is that almost no reaction occurs. It's so reactant-favored, it wants to stay over here as reactants. It doesn't want to turn any of the hydrogen sulfide into hydrogen and sulfur. So the consequence of that, we're just stacking up the layers here, is that the change in reactant concentration is extremely small. Okay? So small that we can ignore it relative to the starting or initial concentration of reactant. Okay? Let's say you went to the bank, you cashed in some, big check that you had, and you had $10,000. And so you're walking around with $10,000, but it's all in $1 bills, because that's what the bank had for you. And you're going to go shopping, and you're going to spend your money, right? When you spend a couple $1,000s on a nice new TV or some furniture or something like that, you certainly notice the difference in how much money you have left. Your stack of $10,000 has been significantly reduced. But if you were walking around a shopping mall or something like that, and $1 or $2 fell off your stack of 10,000, you probably would not notice the difference, right? If you turned away and somebody grabbed 1 or 2 off, you wouldn't notice that $1 or $2 disappeared from 10,000. And you would still think you have pretty close, or you do have $10,000. That's kind of what's happening in this reaction here. Because this equilibrium constant is so small, and this reaction is so reactant-favored, we are going to lose a little tiny bit here. But at equilibrium, when we take into account this loss, this is still essentially going to be 0.8. My $10,000, when I lose $2 from it, is 9,998, but man, that's pretty close to 10,000, right? It's as far as estimating it to somebody else, that's a pretty decent estimate, right? A fair estimate would say it's $10,000. Okay? And we can use that to our advantage to solve this problem. the math gets a lot easier when we plug this in over here. So our equilibrium constant is still 1 times 10 to the minus 7. Now I'm not going to ignore the minus 2x on the product side. If I lose these $2 at the shopping mall and a little kid picks them up who doesn't have any money, they have gained, $2, a significant, noticeable change in how much money they have. So it's all about perspective relative to having some or not having some quantity of a chemical, whether or not the difference matters when your equilibrium constant is small. If you're thinking right now, wait a minute, why didn't I do this last example? My equilibrium constant was not small. 6.35 is not a reactant favored equilibrium constant. So now the math becomes, well, I still got 2x, got to be squared, and x for hydrogen and sulfur respectively. But the denominator is just 0.8 squared. This becomes a much more manageable 4x cubed over 0.64 equals 1.08 times 10 to the minus 7. Those middle terms that made life really hard in the equation that I had written up here a moment ago, they're gone. All right? And this is a lot easier to solve. 4x cubed equals now 6.91 times 10 to the minus 8. X cubed equals 1.728 times 10 to the minus 8. And then I take the cube root, and x equals 0.00259. Okay? Now this whole process of doing this is what we call the approximation method. There are two cases, or two ways to know when you're going to want to use this. When your KEQ, either pressure or concentration, is approximately less than or equal to 10 to the negative 4, this approximation is going to be valid. Okay? That's when you're talking about a small enough value that the reaction is heavily reactant favored. A different way to do this, though, is to consider the initial concentration of your reactant divided by your KEQ. If that is about 10,000 or more, also it's going to be safe to make this assumption. All right. So now if you look back at the last problem, it doesn't fit on either one of those standards. And that's why we could not use the approximation method in that case. All right. Now when we say approximation, our answer really is slightly approximated. If I had solved the long equation that I had here with the x cubed, x squared, x terms in it, my answer in that case would have been 0.00258, I think. So not a very big difference, right? You can see there's a tiny change in the answer here and how correct we are, because this is an approximation. But this was a heck of a lot easier to solve algebraically than that other one would have been if we had attempted to solve it. So it's this trade-off that we make in chemistry, and we're willing to accept this slightly approximated answer in the interest of getting there a little bit faster. All right. Now, we're not quite done yet. Like we did last problem, I need to take the x value and go back and put it into the context of the chemistry here. So what will be the concentration of sulfur? It will be 0.00259 molar. The hydrogen will be double that, 0.00518 molar. And I'm going to actually take into account the 2x, and I'll see that this is really 0.795 molar. Okay? So I have seen a small change, all right, in the concentration. But again, the approximation was made by thinking that this number is about 0.8 still. when we used it in the equilibrium constant expression over here. All right? And so we want to use this ignoring on the reactant side the x or 2x or whatever its coefficient might be when the equilibrium constant is really small here. All right? And you have several chances to practice this through the problems in your homework. But that becomes the first thing you want to look at when you're doing a problem now is what is the size of the equilibrium constant? Can I make this approximation or can I not make this approximation? Okay. All right, let's do one more example then. See what we come up with. Seen this reaction before, N2O4 to give us two NO2s. Suppose the equilibrium constant for this reaction is 5.8 times 10 to the negative 5 at some temperature. Okay. If the initial concentration of N2O4, okay, actually this is going to be the initial pressure, sorry, because that's a Kp. If the initial pressure of N2O4 is 0.400 atmospheres, what is the pressure of each species at equilibrium? All right. So, once again, let's set up a table. Pressure initial, change in pressure, pressure equilibrium. A lot of times these tables, by the way, are called ICE tables. Initial, change, and equilibrium. So, regardless of which variables there, pressure or concentration, they're still called these ICE tables. Initial pressure or concentration, change in that value, equilibrium value. Okay. Again, given the language of the problem, we're told 0.4 atmospheres is the initial concentration of N2O4. 0 is the concentration of NO2 initially. Something will happen, right? There's some reason we're looking at this reaction. Some amount of N2O4 will react. Its coefficient is 1, so I'm going to represent that amount with a negative x, right? Because I'm decreasing the amount of N2O4. That will lead to an increase of 2x because of the coefficient in an NO2. So at equilibrium, NO2 will be 2x. N2O4 is 0.4 minus x, but K is small again, so it will still be approximately 0.4. This is small enough, this 5.8 times 10 to the negative 5, that we're in the range where we can approximate this problem to solve for it. So our Kp expression is how we're going to find x, just like our last two examples. Pressure of NO2 needs to be squared divided by the pressure of N2O4. Kp is 5.8 times 10 to the negative 5. That's equal to 2x, which needs to be squared, divided by 0.4. So 4x squared, because I got to square both the 2 and the 4. That's going to equal, don't have that one written out yet, 2.32 times 10 to the negative 5. So I've multiplied the 0.4 to the left. Divide by the 4, x squared, 5.8 times 10 to the negative 6. Now take the square root. X is 0.0024. Okay? Return to your table now to put your math into the context of chemistry. So what is the equilibrium pressure of each species? The NO2 will be double this value, so 0.0048 atmospheres, the units of pressure. And 0.4 minus the 0.0024 is 0.398 atmospheres. So just a small change exists in the pressure of the starting material here. Because again, this small equilibrium constant means that this reaction is really reactant favored. And we're not going to be making much of the products here. At this point, you've seen several examples of the different types of problems that we're going to solve in this chapter. And you really should be able to do all of the problems associated with Chapter 14's homework assignment, except a couple of questions that relate to something called Le Chatelier's principle and how an equilibrium responds to a shift or a disturbance in it. That's what we'll be picking up with in class the next time that I see you in person. So I hope you've been able to follow along and copy out these examples. Plenty of practice for you in the textbook problems and the worksheets that I provided for you. And so get to work, and I'll see you on the other side of my trip to Dallas.